Hello and welcome back, everyone. Today we'll be doing section 3.2, function types and applications. So in 3.1 we kind of went over what it took to be called a function, and now we'll start actually categorizing types of functions. So the first and most basic one we have is a linear function. That's something that can be written in the form f of x is equal to mx plus b. So notice the variable is just one factor. It doesn't have any exponents other than the implied 1, and it's not underneath a square root, underneath a fraction bar, or inside of a radical. No absolute values involved either. So this is the basic setup for a linear function. Any other type of function is nonlinear, and we'll be categorizing the nonlinears as well. So we'll start with the function p is 1 over the quantity q minus 8. My independent variable on that one is q. So I pick a value for q, and whatever I get will change the value of p, making p the dependent variable. And the name for this one is definitely not linear, since we have a variable underneath a fraction bar. Those, if you recall from our work in chapter 2, are rational. So our next function, k of t, is 2/3 of t minus 7. In this one, our independent variable is t. K of t then would be our dependent variable, the result, what we get from it. And this one, even though we do have a fraction involved, that t is not at the bottom of the fraction. It's just a fraction times t. That is the mx plus b form, so this guy is just linear. Next up, n of x is 5x squared minus 3x plus 8. Our independent variable, we're plugging in x values. The result of that would give us an n of x value. That's our dependent variable, the output. This one, because of the square, this is definitely not linear. We don't have any square on the definition for linear. Square makes this one a quadratic. Our next one, m of t, absolute value of 17 minus 1. Well, then we'll throw a plus, what the heck, we'll throw a plus 2 on there. My apologies. So our independent variable, I'm plugging in t values. Output, m of t. And this one, again, our mathematician friends are not super creative when we name things. This has an absolute value in it, so that's what we call it. And we'll do one more. R of x is square root of x minus 7 plus 4. X is our independent variable. The result, r of x, is the dependent variable. And this is a radical. So those are the most common types that we'll encounter in this course. There are, of course, many, many others. Those are generally the ones that we'll be sticking to. When we have a real-world relationship, these are no longer just functions, they're referred to as models. So mathematical model if we're looking at an application. All right, so our first mathematical model, we'll look at a problem where x represents removing X% of dust from a clean room. So this would be something, for example, where they would manufacture electronics equipment. Dust getting onto the circuit boards that they're putting together can interfere with the transmissions within the chips. So they want as little dust in the room as possible. And f of x is going to be the cost in thousands of dollars. And for this one, they tell us that f of x is calculated by doing 20x divided by 100 minus x. So first of all, the type of function this is, we have a variable underneath a fraction bar. This is a rational. The independent variable for this one is x, and what it represents, removing X% of dust. The dependent variable for this one is f of x, and what it represents is the cost in thousands of dollars. So one thing we can do is sort of plug in some values. For this problem, the author is just giving us some domain values. So we'll start with a domain value of 0. So then our rule, f of x is 20x over 100 minus x. So f of 0 then, 20 times 0 over 100 minus 0 is 0 over 100, giving us a range value of 0. That should make sense. If we want to remove none of the dust from the room, it will cost us nothing, because we are basically doing nothing. So our ordered pair for that one would be 0, 0. So next we'll try to remove, let's say, 20% of the dust from the room. So f of 20, 20 by 20 in the numerator, 100 minus 20 in the denominator. So 400 in the numerator, 80 in the denominator, factor out of 10, 40 divided by 8 is 5. So 20 comma 5. So what that one actually means in words, to remove 20% of the dust from the room, the cost is $5,000. So next we'll try out maybe the 50, f of 50, 20 by 50 over 100 minus 50. So 1,000 over 50, which is 100 over 5, which is 20. So our ordered pair, 50 was our domain value, our range value of 20. And again, what that means in English, though, removing 50% of the dust from the clean room will cost $20,000. So next we up it to 95. So we're looking to remove 95% of the dust in the room. So f of 95, 20 by 95 over 100 minus 95. So we have 1900 divided by 5, which is 380. So 95, 380. So now we have 95% of the dust removed from the room, but at a cost of $380,000. So then you might wonder, okay, what if we remove all of the dust? What will that cost? So f of 100, 20 by 100, divided by 100 minus 100. 2,000, and here's the problem, divided by 0, this is undefined. So there is no ordered pair that will do that. So our model does not work at 100% of the dust removed. So if our universal domain is a set of integers, a reasonable domain for this problem, well, a negative value would mean basically that we are pumping dust into the clean room. Doesn't make sense. We wouldn't want to do that. Values like 101, 102, 103 are also out. The reason for that, x is removing a percent of dust. 100% would be removing all of the dust. We can't remove more dust than exists in the room. So our domain here, we would narrow that down to 0, 1, 2, 3, up to, again, usually we would think up to 100%, but in this model, 100% gave us the problem of division by 0, so we'll go through 99 if we're sticking to integers. So this would be our sort of restricted domain for this problem. Now on this one, notice the cost is going up much more dramatically as we get closer and closer to the 100%. And you can kind of test this out yourself if you try out maybe 10 and 30 and 40, 60, 70, 80, and 90. Test out some more values and you'll see that as x increases, y is increasing much more quickly. So the cost is changing quite a bit as x increases. And according to our model, it's impossible to remove all of the dust from the room. One other thing they can have us do with this, instead of just picking out x values, so saying, okay, I want to remove 20% of the dust, I want to remove 95% of the dust. Another common occurrence in business applications would be, okay, well, the higher-ups came to me with this project, and here's how much money they give us to get it done. So let's say, for the sake of argument, that we're given $180,000 to remove dust. And we want to know what percent can we remove. So first off, 180,000 in dollars, that is an output, that's an f of x. And f of x, remember, is in thousands, so we would replace f of x just with 180, not 180,000, because it was already defined to be in terms of thousands. So it's equal to 20x over 100 minus x. And you may recognize that as a rational equation, one of our friends from chapter 2. Kind of out of room here, so we'll continue on the next page. So 180 is 20x over 100 minus x. So rational equations, if you recall, first we look for excluded values. We already know that 100 is an excluded value. Then we look for an LCD. Our LCD for this one, the only denominator in sight is the 100 minus x. So then we multiply both sides by the LCD. My apologies, that should be a 100 minus x there. Over 100 minus x again. Okay, the reason everything got multiplied by the LCD. Goodbye to our friends, the fractions. So left-hand side, I can use the distributive property. So 18,000 minus 180x is worth 20x. So this one turned from a rational equation into a linear equation. So we'll add 180x to both sides. So that's just the addition property of equality again. So 18,000 plus 0 is just 18,000. And 20x plus 180x is 200x. So we multiply both sides by 1/200. It's the multiplication property of equality at work there. Okay, so 2 of the zeros will drop. We're just sort of mentally factoring 100 top and bottom. So 180 over 2 is 90. So 90 is worth 1x or just x. So what does this actually mean? When it's a word problem, make sure you answer in a sentence. So for $180,000, 90% of the dust can be removed. So make sure you have your units on your numbers. Tell me what those numbers mean. And again, here's another good example of how much faster the cost is going up at the higher end of the scale. We had on the previous page the cost for 95% of the dust to be removed, $380,000. Removing 90% brought us all the way down to $180,000. So $200,000 to remove that extra 5% there. So that's where the companies start making decisions about how much they want to go, how much work they want to put into this. Okay, so our next one, another common application involves x being a time rather than a percent. Occasionally they'll even use a t. So for this next one, we're going over McDonald's restaurants. So for this problem, x is the number of years since 1960, and f of x, number of McDonald's in the world. So on this one, we're told that the relationship between those variables is f of x is 16x squared minus 40x plus 300. So the type of function this is, key here is the x squared. That makes it a quadratic. Our independent variable is x, number of years since 1960. Our dependent variable, then, they called it f of x, and for this one that represents the number of McDonald's restaurants in the world. So next we'll look at how many McDonald's restaurants this model predicts there are in the world today. So this being the year 2020, 1960 is then 60 years ago. So here x is 60. So we would find f of 60, so that would be 16 times 60 squared minus 40 times 60 plus 300. And then just a little bit of simplifying, a little arithmetic. So plugging and chugging, and we get to 55,500 for a predicted number. So the model predicts 55,500 McDonald's today. Now, if you look online, at least as of the search I made today when I made this video, the actual number of restaurants was 37,855. So notice our predicted and model fell quite a bit apart. The reason for that, the author then goes on to tell us that the model was created using data from 1955 through 1987. So our data, 1955 through 1987. This is the year 2020. We are way too far away from our data. When you extrapolate, that's what we're doing. Making predictions is called extrapolating. You want to make sure to extrapolate close to your data. So I would feel comfortable using this data to predict the number of McDonald's restaurants in 1989, or maybe even as far out as 1990, since they do have several decades worth of information. 2020, however, way too far past 1987 for this to be very useful to us. Okay, so that should give you a good idea on how to approach the 3.2 problems. Those are, remember, just at the end of chapter 3. You're also going to try Project 7. That is located in the back of your book. So that's some good practice there as well. So if you have any questions, please feel free to get in touch with me. Otherwise, I will see you again online soon, and hopefully in person soon. We'll see when this is over. In the meantime, please, please, please stay safe out there. Thank you.